Hello, welcome to Bedroom Builds, at a new episode where we will be discussing solutions to the Dining Philosophers problem implemented in Rust. So the topics covered for today will be in general multi-threading, then how we can synchronize between those threads using mutex or mutexisp in plural, semaphore, or MPSC communications. MPSC is for multi-producer single consumer. And since all of this will be done in Rust, there will be some small Rust programming things happening as well. For example, interior mutability and other interesting things. The problem description you can find on Wikipedia. And there is an example implementation found on Rosetta Code for Rust and many other programming languages to this problem. And yeah, let's figure out what the problem is about. So the problem is about 5 philosophers, so philosopher 1, philosopher 2 until 5, sitting on a table, and they want to eat. But in order to eat, they have to use 2 forks. And since there are only 5 forks on the table, so fork 1, 2 until fork 5, they will have to ask their neighbor for a second fork to do their eating. This analogy would probably be a bit nicer if this was about the chopsticks, because with only one chopstick you will have a very hard time eating. Everyone understands once you have a second one, it's a bit easier. Anyways, the original problem was posed with the forks, so I will stick with the forks. So in the example of, for example, philosopher 2, if he wanted to eat, he would have to use fork 1 and fork 2. The problem is, if philosopher 3 wants to eat, he will probably already hold fork 2 and fork 3 to eat. This means while philosopher 3 is eating, number 2 cannot, because fork 2 is occupied by him. One more interesting point for the problem description is the philosophers are not allowed to talk to each other. So philosopher 3 cannot negotiate with philosopher 2 or any other communication like that. Therefore, each philosopher has to find a way or a strategy to acquire 2 forks to get to eat. The problem is, if you program all of them to be eager to pick up the forks as fast as possible, and everyone picks up the left fork first, for example, then the philosopher 1 would pick up fork 1, 2, 2, and so on. And once everyone has his left fork in his hand, they are going to try to pick up the fork to the right to them, but they cannot, because every philosopher already has their left fork in their hand for eating. And then the whole program will not advance, because now we are deadlocked in the position where all philosophers hold one fork in their hand, are not giving it up, trying to get the other one, but they can't because they are already blocked. And this problem needs to be avoided. And that's exactly what the solutions to the dining philosophers problem try to achieve. They try to come up with a strategy. How can you avoid the deadlock, and how can you, in a fair way, try to have all of these philosophers advance with their plan of eating. Right, let's look at the first solution. This whole problem was proposed by a famous computer scientist from Holland called Dijkstra. And he also came up with a solution to it. And his solution is the resource hierarchy solution. And what he is doing is he makes every philosopher use the lower numbered resource first. As you can see, every philosopher has 2 forks available to him, and they are numbered. So philosopher 0, for example, has fork number 5 and 1. Philosopher 1 has 2 and 1. If we now stick to the rule to pick up the lower numbered resource first, then 1 and 0 will pick up the fork 1 first. And this helps with resolving the deadlock problem, because out of those 2 philosophers, only one will win and really pick up fork number 1. And if, for example, philosopher 0 wins, he can pick up fork number 1 and 5. And why can he do that? Because philosopher number 4 will try to pick up fork 4 first, therefore fork 5 is free. And let's suppose that philosopher 1 wins the race and picks up fork number 1, then he will probably lose the race to philosopher 2 and so on. But since philosopher 0 couldn't pick up his first fork, he will not try to pick up the second one because he failed. This now means that this philosopher 4 gets to pick up his fork lower numbered 4, and it's free, the fork number 5. And whenever then one of these philosophers that won the race of picking up 2 forks has finished eating, he will return the forks to the resource pool. And in the case where the first one that could advance was number 4, philosopher 3 can start because he has fork 3 in his hand and will pick up fork number 4. And this is how you avoid a deadlock, and at least your program will advance. In the worst case, maybe in a slow fashion, but better than a deadlock. So in order for this to work, each of those philosophers will have to acquire 2 mutex guards. Once he holds those, he is allowed to actually do his work, in our case, eating. Let's look at how this looks in code. So here I am going over the Rosetta codes example, which implements the Dijkstra solution. I have modified it slightly because here Clippy would tell me that it's not necessary to use left colon left and right colon right. And here I changed from thread sleep ms to thread sleep using the new function signature where we can pass duration. In this solution, we will be using mutexes, as already told before, but in order to send the mutexes off to other threads, we have to use an atomic reference count. Then we use threading, and the duration I already mentioned with the sleep. The structure holding the philosopher information holds the philosopher's name and an index to the left and an index to the right fork he will try to pick up. The implementation of the constructor is therefore fairly easy. We pass his name and the forks he's responsible for. And we implement a method where we will pass a reference to the table. On the table he will find the forks. As we can see, we try to pick up the left fork first and then the right one. So this second line only happens when we actually managed to acquire the lock on the first line. When we have those two, you can see that we print out that we started eating. Our processing is fairly easy. It's just sleeping for a second, and then we are done. The table has the forks. The programmer of the solution found on Rosetta code chose to create the table forks as a vector of mutexes that hold no meaningful data. It's just the unit type. And the reason is that we only care about the index of the fork, if we can acquire it or not. And therefore, we don't need to actually guard a specific data structure behind the mutex. Let's scroll a bit down in this code. So here we can see the main function. We initialize the table with the forks. Since we have 5 philosophers, we create 5 mutexes. Then we set up the philosophers, and you can see first philosopher gets the name of a philosopher, and he's responsible for the forks 0 and 1. Then the next one gets forks 1 and 2. So this now means that this Bauch Spinoza will share fork 1 with Gilles Deleuze. And this keeps going. But you can notice in the last line for Michel Foucault, he changed the order of the arguments, because normally it would go 0, 1, 1, 2, 2, 3, 3, 4. It should be 4, 0, but it isn't. And that's the trick to avoid the deadlock, because the first fork that he will pick up is the lower numbered one, the left one, and then the higher numbered one. If we were to reverse that, we have a chance for a deadlock. Now into the technical part, setting up the threads. This is using the functional programming style that Rust allows. So we have the philosophers that we have just initialized. We use the into iterator, and we map over every p philosopher. And then for every p philosopher, we are now cloning the table, but we don't really clone the table because up here, behind an atomic reference counted smart pointer, is the table. And that's why we are cloning the arc and not the whole table. And with this, we can now move the philosopher into the thread that is spawned, and we can also move the now cloned reference to the table without running into a problem, because this map will be executed for every iteration step. Therefore, we have to do this cloning before we spawn the thread to hand over the reference to the table. This is then collected into this handles vector, and that is important because just doing that will actually not do much. We have to join on those thread handles to actually wait for their results. And this can be done here. We are looping over the handles and we join all of them, and we hope that they don't fail. That's why we are using unwrap. Let's run the code. So we can hop into the shell on the left and run this Rosetta code example. I'm using the release build to make sure that this is using the maximum performance possible. And you can see it works. All of the 5 philosophers start and stop eating. What we can try now is provoke the deadlock. And let's run this again, because now we are in the deadlock configuration if you want. But we can see that actually it still works. So why is that? Well, on modern computers, acquiring the 2 locks is very, very fast. So if you look at the code here, where we are getting the left and the right mutex, we are doing this in sequence. So all the threads are starting one after another, and they right away start with this eat method. And apparently starting up a thread is slower than acquiring a mutex guard. So even in the deadlock configuration, this kind of works out. And this is the whole reason I actually came onto the topic of the Tiny Philosophers problem. A fellow programmer asked me, well, I followed the tutorial and I coded this up, but I cannot get it to deadlock, so I'm not sure if this actually is a real problem. Well, let's make the deadlock happen. This can be done by introducing a small delay right after we acquire our first fork. So if we go here and we only wait for 1 millisecond after we acquire the first fork, so the left one, then we wait for a millisecond and then we try to get the right one. This 1 millisecond will be enough time for other threads to start up and already pick up the fork. Let's see what the consequences of this is. Wait, let's clear the screen. So we are running again this Rosetta code example with the bad configuration, and you can see nothing happens. The whole program doesn't advance. There is no output. It is deadlocked right away. So we stop this one. We keep the 1 millisecond pause, and now we make basically the proof that Mr. Dijkstra found a good solution. We save the new configuration where we now reconfigure the first fork to be the lower numbered one, and we run the code again. And it works. Now we can see that They are eating in a sequence because this 1 millisecond is actually fairly long pause when it comes to computer processors. And one philosopher eats after the next one, which is not optimal because normally they can eat in parallel, or at least some of them can, because we have 5 philosophers, 5 forks. So in theory, if 2 philosophers eat at the same time, 4 forks are in use. So that is theoretically possible. This means normally we should be done in 3 seconds because we can have 2 philosophers eat, again 2 philosophers eat, and then the 5th one. This would be the fastest time in our minimal implementation with the 1 second sleeping. And this is no longer happening with the 1 millisecond sleep. The thing is also, this is not a good API because the programmer that uses this philosopher struct has to know to put those two in the right order. Otherwise, he actually is prone to a deadlock. So I came up with a solution that takes this as inspiration, but makes it a bit nicer to use. So let's hop to the solution. If we now look at the code in here, we can see that there's not too much difference. This is already the same. This stays the same. But this is what I find a better API solution, because we still take the left and right fork as an argument to the constructor, but internally in the constructor we make sure that the left fork is the lower numbered one. For this we are using the standard comparison min, and we take the minimum of those two into the left, and we take the maximum of the 2 arguments for the right fork. This way you can badly configure left and right, and it will still work out fine and not lock you up. I guess the idea of the Rosetta Code programmer was to easily show that you can end up with a deadlock. But since the original code, by swapping 2 numbers, doesn't really make this apparent that you are deadlocking, that doesn't really help. So I would prefer this solution. Rest of the code is the same. The only thing is, you can see here in the comment that we don't care that this is the bad configuration because the constructor will fix it for us. So let's run that extra example to see if that's true, that it really works for us. Let's run that extra example, and we can see it works even though we have the bad configuration. And we can also see that here, because we don't have the sleep after the first acquiring of the lock, there are 2 eating at the same time, and then again 2 eating at the same time, and then the last one. This makes this finish in 3 seconds. So this Dijkstra code will be then available on the GitHub repo. Let's discuss the next option, how you can solve this. So on Wikipedia you have the explanation of how the problem is proposed, but also potential solutions to the problem. I tried to implement all of them. Let's see what the next one brings. So we went over the hierarchy solution. Now we can look at the next one. So the next solution is the arbitrator solution. This means that there is a central point where the philosophers have to acquire their resources from. The advantage is you no longer have to deal with this, I have to be able to get 2 mutexes before I can advance, and therefore the deadlocking problem goes away, because the mutex is exactly helping you to avoid 2 processes accessing the same resource at the same time. So now this single mutex will guard a waiter, for example. So if they are in a restaurant, there will be a waiter, and they have to ask the waiter to give them a fork. And then, while their second fork, and once they have the 2 forks from the waiter, they can start to eat. Let's scroll down a bit. So here you can see the table of the philosophers. And what they have to do now is they no longer have the forks on the table. They actually have to ask the waiter. So the first one would have to ask for fork number 1 and fork number 5. And the waiter will react to this request or not. So one solution how you can implement the waiter is the waiter will give out forks if he has forks available, unless he only has one more fork left. Then there is a similar restriction as we had in the Dijkstra solution. The waiter will only give the fork to a philosopher that requests it for his left hand, or if you are right-handed, then for his right hand. But the last fork will only be given to a philosopher that asks for a specific hand. And this way you avoid a deadlock as well, because this way the waiter guarantees that at least one of them can advance. So in best case scenario, if we programmed the waiter to give the last fork out to a philosopher with the right hand request, the first one will request now fork number left, and all the others will request some forks, but at some point the waiter will run out of the forks and only have the last one, since the other philosophers will ask for the left fork first, and only philosopher 1 will ask already for his right fork. This last one will be given to the philosopher 1 and he can advance, and then from there we never run into a deadlock. So let's look at how we can implement, for example, this strategy. There is many ways to do this, so I might have even chosen a broken one, but we can discuss that in the comments. Let's hop over to the code and see what the arbitrator solution looks like. For the arbitrator solution, I copied over the code from the original Rosetta code example. So here we do not make sure that the lower numbered fork is used, because now the arbitrator is supposed to fix the locking problem. Let's hop down first before we go over how the philosophers eat. So what I've created is, to make this a bit easier and obvious to read, is I've created an enum fork, and there is defined if I'm requesting a left fork or my right fork, and I have to specify which fork I want. So these enum variants also hold values. The left one holds a number and the right one as well. This way we can ask the waiter for a fork, let him know which hand we want the fork for and which number we want to have. Then I make a type alias for that I call forks, which is just a vector of a Boolean. This as well can be set up in many ways how you want to store the forks, but this way I found very easy to read, so I will use that. Then now on the table we no longer have forks, we have the waiter that is holding the forks behind one mutex. And now we implement the table. Here I re-explain the strategy. So only the right hand, so the second hand, will be dealt with the last fork if requested, and not any other if there's only one more fork left. So the table take fork implementation will now get a mutex card on the waiter. Then we figure out how many forks are available. We do that by iterating over all the forks, filtering all those ones out that have the flag true, meaning they are no longer available because they are reserved. This is done by using the exclamation mark for negating the Boolean, and we have to dereference it because the iterate will give us a reference to the data inside the vector. Once we have filtered all those out, we can count, and then we know how many forks we still can give out. So with this number, we can now actually run our algorithm, but we need one more thing. We have to create code that actually reserves a fork. How does that work? Well, you can only reserve a fork if it's not already taken. We make a small closure that takes the index of the fork in our vector. Then we check for the forks index. If it is false, we actually set it to true, and our closure returns the value true. If the fork is already taken, we return false, and we don't modify the fork state. Now we are matching against the fork request from the philosophers, so which fork they wanted to take. If you want to take a right fork, then you directly get your fork. And if you request your left fork, now we check if there are still more than one forks available. If that's the case, yes, go ahead, you will get a fork. If that's not the case, I will return false, because I will not even try to give you a fork. I only react to right fork requests for that. This is the strategy for handing out a fork to a requesting philosopher. We can now scroll further down to see what happens if we call a return fork. So a philosopher that finished eating will return the fork to the waiter, and he will call this a return fork method. We lock again the waiter because we need to modify the data structure behind it. And then all we do is we set the fork index to false, meaning it's available again. Here you can see on purpose we set up in the deadlock position our philosophers. We also again create an arc for our table that now holds the waiter with only one mutex. We create a range over the length of our philosophers because we have to match the number of philosophers with the number of forks. We use an into iterator, and we map every instance into false. We don't care about the value coming in. We just use this to have the correct length for our vector, and we collect this into our forks type. So once we have that, we can again create our threads. We again use the iterator to map. We clone the table, so this all stays the same. We have our threads spawned, and we start the eating. Now let's look at the eating of the philosophers. Here we have the eating strategy of the philosophers. We will print out that we are asking our waiter, and we will tell who we are to the end user. Then here we have named loop. The auto loop will try to ask the waiter on the table if he can have his left fork. And if that works out, we now enter a busy loop where we try to now get a hold of our right fork. And once we have our right fork, we can start eating. This is our sleeping for 1 second that all philosophers have done so far. And once we are done eating, we are now returning our 2 forks. And here is a cool trick that Rust can do. So we named this loop with the tick eat. When we have an inner loop, in order to break out of both of them, we can actually tell break which loop we want to break. So we use the label eat. And this way we stop eating and the philosopher is finished. The disadvantage of this algorithm, of course, is this busy loop trying to get a hold of actually already the first and the second one. So we are hammering the waiter with mutex requests and then ask the waiter to check if he actually has something available for us, and if yes, give it to us. But this kind of shows one idea of how you can use this strategy. Let's run this code and see if it actually works, because we have seen that it is badly configured. So Arbitrator, and we can see that it works out. All of them are eating. So on the left we can see that the first one starting to eat is Karl Marx, and then it becomes a bit more of a mess because the rest of them are asking the waiter, and then one of them starts eating, but another one asks for the waiter, and then one guy stops eating, and then another one starts, and you can see that this is kind of intertwined, but also not efficient because of this busy loop. There's one more solution that actually makes sure that there is one less person on the table. Let's look at this one. For this we hop back to the presentation. So we can also solve this by limiting the number of diners at the table, or in the table. That's a stupid formulation. This can be done using a semaphore. A semaphore is a synchronization construct that allows you to give you a certain amount of how many processes or threads are allowed to access a data structure at the same time. and sometimes this can be useful. A mutex will only allow one single one to access it, but maybe you have an algorithm where you can make sure that 4, 5, 10, whatever can keep going and there is no problem. And in our case, we will use a semaphore to make sure that at max n minus 1 philosophers get to eat. So in our case, with the 5 philosophers, we will only have 4 eating. And this way we can make sure that none of the philosophers is hungry. With this, we can see that the fourth one potentially, depends on how fast he is asking the semaphore, will not eat. But the ones with the index 3, 2, 1, and 0 will get to eat. And since each of them needs 2 forks, we can see that, for example, philosopher 0 and 2 can eat at the same time. And once they are done, potentially 1 and 3 can eat at the same time, or because by then, when one of those has finished, philosopher 4 will join, but then 2 more can eat, and then the 5th one. Let's hop in to the code for this one. So now for the n-1, we are using an external crate because the semaphore was deprecated in Rust 1.7, I believe, a long time ago, because they realized that people confused that with a system semaphore, and it was not really used widespread back then. Therefore, it's no longer in the standard library. There are people that extracted the code from back in the day. You can load this one. I simply used the first one that I found to give an example of how you can use a semaphore. There are many implementations out there, and this is also much trickier than a mutex, because here you can make sure that the semaphore is fair, for example, making sure that it treats requests in order, or it could also actually be on purpose unfair. So there's many requirements that you may have for your application. It doesn't make sense to have the one and only available. We can see that our philosopher stayed the same, and also on purpose we do not help with the lower numbered fork, because we want to prove that even though in the wrong configuration, we can now fix this with our newly acquired technique of only having 4 eat. We keep the same code that has the double locking, so like the original Rosetta code example or the hierarchy solution, but on purpose broken. We ask for the left and for the right fork, and we eat. So we still have the 2 mutexes that we want to lock, plus the semaphore if you want. So where did we add the semaphore? Just to show you again that here we are misconfigured, and now we get to our semaphore. We are setting up our semaphore again behind an arc, because we have to share it between multiple threads. Here we instantiate our semaphore. We compute the n-1. So here you can see we do the length of philosophers minus 1. And again, the unit type, because all we care about is limiting the number of philosophers eating and nothing more. Once we have that, we can clone the arc as we did before with the table. But since we now have to also provide every thread with the semaphore, we clone this one too. So now we are back into our busy looping. We create a loop that then tries to access the semaphore. If this works out fine, we eat. Once we are done eating, we break the loop. This is really just to show that the semaphore will help us solve this problem. This is probably also not the most efficient one, especially if you're coding embedded and want to save battery lifetime. Okay, let's check though if keeping only 4 eating at the same time actually solves the problem. So we can hop again on the left, and we can run the n-1 example, and we can see that it works out. This is also a solution to this problem, and we learned about semaphores. Now we can hop over and discuss the last proposed solution that we can find on Wikipedia. Is I hope I'm not mispronouncing their names, the Chandy and Misra solution. So those two computer scientists came up with this one. They are cheating a bit because the original proposal said in this problem the philosophers are not allowed to talk to each other. But they came up with a strategy where this can actually be done by having them at least talk to each other when it comes to requesting the forks. I implemented that using the MPSC channels, so multi-producer, single consumer. For this implementation, I chose to go full out on every feature that Rust offers, just to on purpose show how you can do this. So there is for sure a way you can solve this actually without using channels and still sticking with the same idea. But I've basically literally translated the problem's solution into code if you want. So down here you can see with a weird short form what's going on. So every philosopher has his own block where he is keeping his resources. So this is the processing that's happening. What we can see is that every philosopher has a receiver end of the channel. And a single consumer means that you only have one receiver, but you can have multiple producers of messages. And this is used to the effect that if we, for example, look at the philosopher number 2, he has his receiver that actually receives messages from philosopher number 1, so one of his neighbors, and philosopher number 3, the other neighbor. You can see the connection coming in like that. And this is what's happening for every philosopher. So the number 4, for example, talks to his neighbor number 3, and this super long arrow all the way from here from philosopher number 0. So everyone gets to talk to the neighbor, and this means that, again, back to philosopher number 2, Phil 1 can request his fork from his neighbor and also from his other neighbor. And once he successfully acquired the fork, he can eat, and that is true for all the other philosophers as well. A big part and important part of this Chandy Mistra solution is there is a concept of forks being dirty and clean. So a philosopher can eat once he has a dirty and a clean fork, or 2 clean ones or 2 dirty ones, whatever, but he will never give away a clean fork because that means he hasn't eaten yet, meaning he is starving more than the others. He gets to have the next fork coming in and eat, and not give it to another philosopher that may have requested it from him back maybe. This way you kind of solve all the problems with starvation, so one philosopher getting to eat super late in the task, or the fairness problem, meaning everyone has to have the same chance to get to eat. And this clean dirty labeling makes that possible. So this I try to do with coloring. The strategy to set up the table for this communication problem then also is you hand out a dirty fork to every pair of philosopher, but you give it to the philosopher with the lower number. And you can see here, I visualize that with this violet color. Philosopher number 3 gets the fork that is between number 4 and 3. Then number 2 gets the fork that is between 3 and 2, and so on. And now that's the point. Between philosopher 0 and 4, the fork also goes to philosopher 0 because he has the lower number. So now the starting condition already is this philosopher 0 has 2 dirty forks, and therefore there is already an imbalance. So either this one starts eating right away because he has 2 forks, or when he gets asked for one of his 2 forks, this makes actually another philosopher able to eat either 1 or his neighbor 4 potentially, and therefore there is no deadlock happening. So this is all kind of complicated, which is also visible with all those arrows going around. Let's look at how we can implement that in Rust using the communication channels. Now you note that there's no more mutexes and no more semaphores in use. This is all now synchronization using the MPSC channels. And why does this work? Those channels are implemented as FIFO queues, so first in, first out. That means, let's see if I can draw that somehow. That means if there is now the philosopher 1 is talking to philosopher number 2, he will send a message that goes into a queue, and once the message came in, he will put the first message into the top end of the queue, and this will also be the first thing that the philosopher 2 will pick up and read. So if there are multiple requests coming from, in our case, philosopher 1 to philosopher 2, it will be queuing up in those other buckets. You can actually even give those channels a size, so you can limit the number of messages that can be queued for the reader, because maybe number 2 is too lazy reading or cannot do it. Then you can make sure that those channels cannot overflow. And once the philosopher has finished eating, for example, number 2, he can start picking up those messages and processing them. They are sent in the good order to the other reader, and that's how you can synchronize between 2 threads and also exchange information, which is exactly what we'll be doing. So let's hop over to the code and see how this works with this solution in Rust, or can work, because of course, again, there's many ways of doing this. Up top, I have the description found in Wikipedia to remind ourselves how this works out. One extra feature that I'll be showing in this code example is interior mutability that we will have to use. Then, out of laziness, B-tree map, hash map, and a vectec. So B-tree map is more or less a hash map from the idea, but I get to profit from the fact that their iterators or keys method will give me the keys in an ordered fashion, and that is important for the algorithm, so that's why I chose this one. It's complete overkill, but I still used it. Then hash map is like a dict in Python, if you know, so you can put a key of a certain type that holds a value in there. And the vectec is a vector that is a double-ended queue, so that's why DE and Q. This means that I can put values inside this vectec, and then I can take them out either at the end or at the beginning of the vector. Doing this with a normal vector would lead to a lot of new allocations in memory, and that's not efficient. And also there's no real good API behind that, so I chose advectec for this solution. The standard library provides these MPSC channels, so again, multi-producer, single consumer. And again, threading duration is the same because we still eat for 1 second and we use multi-threading. Now coming to the literal code translation of the solution from the text. We are using an enum that denotes the state of the fork, so it can be dirty or clean. If you want to, you can use a Boolean flag for that, but this speaks way more to the programmer when he sees it. Then we have the fork again. This time we actually have a struct for the fork that holds the identifier to know which number the fork has, and the fork has a state. It is dirty or clean, so we store that information inside the fork as well. Here we can see we derive a debug and a partial equality for the fork state. Debug makes it printable, so we can see a name for our enum, so we don't see true false for a boolean or whatever 0 1. We actually see dirty and clean printed out. That's kind of useful. And partial EQ can be used in an if statement. Down here we do a custom implementation of the debug trait. The reason is that the output on the terminal will be shorter, and we don't have all this extra information, curly braces, and some data that we don't want to see. I will scroll down because my head is in the way. So what we do for implementing a custom debug trait is we implement the format method. This you can copy paste from the code inside the documentation. And then all we have to change is the body of the code. So here I make a smaller representation of the dirty and clean text by only returning dirty and clean. And then I also don't print any curly braces. I just have fork, its ID, and its state. Now we implement the actual fork. So we want to create a new fork that is of state dirty. As said, the initial state will be dirty to create our table setup. So my constructor got this name. The constructor returns self. This self is referencing to the type we are implementing. So this returns a fork. And here I can reuse that. So if I were to rename fork to chopstick, the code would not have to change because self then would automatically do chopstick for me. Another thing we need is fast access to know if it's dirty or not. And then we can clean fork. Here we have to now provide a mutable reference to self to be allowed to clean it. And the same is true if we want to dirty up the fork, we have to also take a mutable reference to self. Initially, when I coded this up, I was kind of lazy and only put the fork behind an option like that on to the table. But then I realized I have to track that I requested this fork already to not bombard my neighbors with the messages for no good reason. So I created a new struct called the fork storage where I track if I requested for this fork or not. And then I'm still putting the fork behind an option because I can have a fork or I don't. Therefore, I use the option struct. And here comes the interior mutability already. I cannot simply use requested boolean, as you will see later down in the code. I will actually have to hide that behind the cell, because otherwise the borrow checker will not like what I'm trying to do. Then again, a custom implementation for the debug output of our fork storage. I'm again just writing out that I am a fork, which ID I have, as you can see here, which state I am in, and if I have been requested or not. This can be useful when you write a debugging output to see if the message passing actually does what you want to your data structs. If the fork that I'm holding is actually not there, then I actually can hard code that, I have no fork. But if I have requested the fork or not is important information, so I still put that out there. And up here, I'm formatting the boolean into something that is human readable, so I can either have it requested or not yet requested. Now we get to the point where you can see why I told you that I initially had this behind an option. You can see with the isSum implementation and the take, for example, that I didn't want to change too much of the code. I'm now hiding this behind my new fork storage. Let's scroll down to the fork storage. So the implementation is, of course, the constructor again with the same trick. We use the self to construct it. And by default, we have not requested the fork, so we use a false inside the cell. And of course, the fork that has been handed as an option to the constructor. Then the isSum is simply forwarding it to the internal option. So is the take. So we can check if a fork is dirty. For this, we go to our fork provided as a reference, and then we use a map or. So if we don't have a fork, we can claim it is not dirty. And if we have a fork, we can ask the fork to return its information. We can make a fork dirty. This is then the same, but this time we have to take the reference as a mutable reference, unwrap the option that comes out of this, and make it dirty. We will have to check if a fork needs requesting. There are two reasons why we want to do that. We haven't yet requested it, or we don't have a fork. So we do this combined check. We don't have the fork, or we haven't requested it yet. And then we can also set a fork requested. But here we have to make sure that this is not a mutable reference for the borrow checker. This is why we use the interior mutability. We can now use the cell that is requested and use the cell's set method to set it to true. This means that inside this method, I can actually modify the state of my struct without exposing that information to the compiler that doesn't like sharing mutable references in a loop, for example. Now we get to the messages that we will exchange over our channels. So we have this enum called fork message. Inside there we have two different message types. One is a request that takes two informations. Both of them have a usize, so this will be the request of which philosopher actually requested that and which number of fork they want to have. And then we have a delivery message that actually hands over the fork to the philosopher. Now we get to our struct. This code, as you can see, is way more elaborate than the other stuff we've built so far. This again has debug implemented. We have now the philosopher ID. We give him a name. Then we have the multi-channel receiver that receives a fork message. Then every philosopher, as on the drawing, holds a receiver from the MPSC. And we are transporting fork messages. We have to tell that information as well to the compiler. And then we have our neighbors. That is a hash map. Usize is just the number of the neighbor, so the ID of the neighbor. And of course, the sending MPSC channel. And again, we exchange fork messages. Then we have now our forks. They are stored in a B-tree map because I want to pick up my lower numbered fork first. And therefore, I use the B-tree map because the iterator will automatically iterate starting with the lower numbered fork for me. So this is the fork ID, and then we use our fork storage. And me as the philosopher, I can receive a request for a fork that I don't have or that I don't want to give up. If I don't have the fork, I cannot give it to the other philosopher. And if I have the fork, but it's clean, I will not give it to the other philosopher. But I know that he wants it. So in order to remember that, I built this request queue. That's vectec. And this one I can then process after I finished eating. So this also holds the info who wants the fork and which one. Now let's implement the philosopher. Now the constructor is much more complicated. We have to pass our receiver to it, the name and the ID of it. The rest is just initialized by default. It is an empty hash map, empty B-tree map, and an empty vectec. So for every neighbor, you get a sender. So every philosopher has two senders that I will insert into our hash map. And that's the philosopher ID to know which neighbor ID you want to talk to. And then the sending channel is stored in there. Same is done with the forks. I actually make sure that nobody gets handed more than two forks. And we store the information, whose fork is that, and then of course the fork inside. Then the philosopher also wants to eat. This we'll look at a bit later. If we scroll down to those, we can see that we have a helper function that can identify the ID of the left neighbor and the right neighbor. So normally it is your own ID minus 1 would be the one to your left. But if you are the number 0, you will have to actually figure out what's the highest key in your neighbor's information. And then the neighbor right, I implemented in an even crazier way. So now I am going over all neighbor keys and I'm finding the one that is not my left neighbor. This of course can be done way more efficient, but I kind of try to stick to, even though this is already cheating, to the problem proposal that every philosopher does not know about his environment. So he doesn't know about how many philosophers are on the table actually. And therefore I cannot, with this principle, do a math that would easily compute the right and the left neighbor, because I don't officially have this information how many philosophers exist on the table. So we are cheating with this solution, but not full on. Then here we are handling the requests that are coming in over the message channel. We will see this function later. And this is basically what the philosopher is doing. He's going into an infinite loop where he tries to eat. If he can eat, well, he does it. If he cannot, he will use the handler requests, and in there he will process the messages that come in through the channel. Let's go to the main function where we set up our whole problem, and then we can look at how the eating and message handling is implemented. So in order to set up our table, we first just use the names of our philosophers. We make an empty vector to hold the senders of the individual philosophers. And then we actually now create our vector of philosopher structs. Therefore, we loop with an iterator over our names. We enumerate them, so we have an ID that matches where we want to put the sender. Now we can map the index from enumerate and the name into creating our philosophers. So first we have to create our channels. This creates a sender and a receiver. The sender we push into the vector. If we simply push that at the end of the vector, it will have the same index as the philosopher does in the names. Then we create our philosopher with the ID number, with his name, and important, the receiver. So this is the receiving end of the senders that are available. Then we collect those into our phils, the philosophers. Once we have that, we can figure out how many philosophers do we have, and then we can figure out the highest ID of those philosophers. And now we can continue with our magic of setting up the table. We now wanna give every philosopher the respective senders that he needs. So we loop over the senders with the iterator, and again we enumerate to have the index and the sender. Now we figure out who's the left and right neighbor. Once we have that, we can now give the philosopher on the left and the philosopher on the right the respective sender that we now have in our loop instance. We have to clone the sender, because otherwise we cannot hand it off to multiple philosophers. So now actually we will have one sender that is unused, if you will, inside our senders vec, and we have the clones in each of the neighboring philosophers. Then we decide who gets the fork. So the neighbor with the lower index gets the fork. This means we set up this philosopher's fork and the second fork that he will need to request to work with. And then on top of this, we write again a new setup for the fork, because now we have to hand out the dirty forks to the correct philosopher. As you remember from the start, one philosopher will get 2 dirty forks and one of the 5 will get no forks whatsoever. This way we avoid a potential unfair starting situation. And from here we can now create again the thread handles. So now we can loop over mutable philosophers. We can push the thread and run the mutable philosophers. And once they are done, and then here we join the thread handles. Why does the philosopher have to be mutable? Because the run method is requesting a mutable reference because it changes internal state. So let's hop into our run method again. For remembering, we eat and afterwards we handle the requests. Let's jump up to the eat method. Luckily, eat fits on the screen. So basically, we can eat when we have both forks available. So all we have to do is we have to ask the iterator if all forks are available. And if they are, we can start eating, because we don't care about in which state those forks are. They can be dirty or clean. We will eat in any case. Then this is our sleeping. Now we are creating it from seconds and not from milliseconds, but it's still 1 second. And then from there, we are making our forks dirty because we finished eating. This is done here. We are using an itermute to get mutable references. And once we have that, we can make the fork dirty. Then we announce to the public that we are done eating. And what we do now is we go over our request queue. So it could be that we held, for example, clean forks, and now that we have dirtied them up, we can actually hand them out. So that's what's happening here. So we get the first message by pop front. This makes sense because if we push back the new messages to the double-ended queue, the first one will be at index 0 and the successive ones are coming later, so we are popping from the top. We get the first request queues information out of there. This tells us who wanted which fork ID. Then we check again, it's a double check, if the requested fork ID is dirty. If it is, we can actually hand it out. That's what we are doing. We're getting a mutable reference to our fork ID. We take it. That means we get the value inside the option returned into our fork. This one has to be mutable because we have to clean it when we hand it out. And after this take operation, the option will now hold none in the place of our fork. So we no longer have our fork. We have cleaned it. Now we can send it off. So all we have to do is we go into our neighbor's information, use the ID of our neighbor, and send off a fork message of type delivery. And this one holds the fork that we just cleaned. So this one is sent off. If we can not eat, so this condition is not true, we end up in our block down here. And here we now have to go over all forks that we have, and we want to filter out the ones that need requesting. We only ask for one fork because we are nice. So even if maybe we are missing two, we are not creating two messages right away. And once we have done that, we are now looping over each of those forks that we want to request. In our case, it's just one. We get the fork ID and the fork information. So fork is no longer correct. It's actually a fork storage, as you can see here in the type hinting. And here we are now assigning the philosopher ID to being the left or right philosopher, decided by the fact if the fork ID matches the philosopher ID, because every philosopher will have a fork with his own number basically, and the neighbor's one he wants to request. And then we can actually send off the request messages. All we have to do is ask our neighbor by using his philosopher ID and sending him a fork message of type request that now holds our own philosopher ID and the fork ID that we want to request. Now that we have requested the fork, we set it to requested, and that's the whole reason that we need the interior mutability, because you can see that we are iterating over our forks in the non-mutable fashion, and we have to do that, otherwise the compiler will complain. If we were to use iter_mute, it will explain to us that we are borrowing, for example, here our own struct read-only, and then here we would have a mutable borrow that would be needed, and this mix is making the Rust compiler uneasy, so we have to hide it from him with a cell, and therefore we can actually modify our fork requested status in a non-mutable iteration loop. Just to remind ourselves, the eating process can send off either delivery of forks to other people because they have received the requests that they couldn't fulfill, but now they can because they finished eating, or we want to eat because we don't have forks and we request those forks. Now we can scroll down to the handle requests, which we can go over here. So this also takes a mutable reference to self. And here we can see how this works receiving a message. We use our receiver, the receive function, and this one blocks. So if there is no message coming in, then this will actually stall until there is a message coming, and there will likely be one because someone will request a fork from us or will send us a fork because we requested one. And that's how the philosophers get to sync up and actually work together to eat. If the receiver does not receive an OK message, that can happen. For example, if the sender goes away, then it's impossible for a message to come in and we have to handle that error. But we are assuming that our philosophers stay alive. So we are only handling the if a message is OK branch. But now that we have the message, it's of this enum type fork message, we match that against the enum variants. So we have the variants where we are being requested a fork or we receive a delivery of a fork. Let's quickly go over the delivery. That's the easier code, right? The delivery holds a fork for us. All we have to do is we have to insert into our B-tree map a fork at this ID location, and we use our fork storage to create a new fork that we actually hold. So we use some fork as the argument to our constructor. And now back to the requesting. So if there is a request coming in, we have to check if the fork that we have received a request for is dirty. And if that's the case, we actually can send it to our neighbor, because that's how the rules go. If you have a dirty fork, you have to give it up. That again does the same trick that we have seen already. We get a mutable reference to this fork's ID, and we take it out of the option. Then we have the fork in our hands, but it has to be mutable because we need to clean it before we hand it out. And then again, we create the fork message of type delivery with the fork inside. Now on the else branch, this means we are not allowed to send out the fork. We have to attach this to our queue. Now here's a double check to make sure that the queue doesn't grow too much. We actually look inside the queue with ether and the any method. This small closure makes sure that we do not already have the same request for the same philosopher with the same fork ID. If we don't, we can actually push back this new request for the philosopher and fork ID. So now we have two measures to make sure that there's not too many messages floating around. One is we track if we have requested the fork, and the other one is have we actually pushed too many same messages to the request queue, which would be useless. If you remember the loop being handled after eating, we would pop off the messages. So if there was 5 times the exactly same message, we would then process something that doesn't make sense because we already have sent off the fork to the respective neighbor. Let's see if this code also works by running the Chandy Mistra example. And here we can see that they are now successfully eating. And this is an infinite loop. I have not implemented a way to stop those philosophers from eating, but we can quickly check. At the beginning, we have the IDs of the philosophers. So number 1 is eating, 4, 2 is done, 0, 2. So we can see that actually every one of them gets to eat every now and then. And we can see up here, we are back to 0 and 4. With this debug output, we can also see that the forks are handed out correctly, even though after they changed the messages. So if we check, for example, philosopher 3 will have his own fork, number 3, but also his neighbor's fork, number 4. And the ID of the fork matches the index of the forks that he's supposed to have. And this is true for every philosopher. If you want to stop those philosophers from eating, you would have to potentially create one more thread that is waiting for a certain condition to happen, and then we'll send off a message to the individual threads to tell them to stop working. One idea could be you create one more message variant of the fork message that says stop eating, for example, and then this extra thread talks to yet another clone of the sender channel to each of those philosophers. And this and in there you can wait for a condition like, I don't know, 60 seconds have passed, or you can also make this over the top. You create yet more MPSC channels where the philosophers announce how often they have eaten, and you will make them stop after every philosopher has eaten 5 times. But this is left as an exercise to the viewer. Thanks for watching. I might make another episode where all of these implementations are done with async and not threading. If this is of interest to you, let me know.